Hello everybody, SirBased here. Today we're going to be learning statistics with a little textbook called Learning Statistics with R by Danielle Navarro. The copyright for this is Creative Commons. I am allowed to do this as per the law. My reason for starting this live stream is so that I can essentially improve my videography skills, and also since I was already learning statistics and teaching myself statistics, I figured I may as well just record myself on learning statistics. What can you expect from this? Frankly, you can expect a very boring live stream with me not really talking all that much. I am doing this primarily just so that I can get in the habit of YouTubing and so that I can get better at it. Without further ado, or actually, let me say this first, and I would like to talk a little bit about my experience or knowledge with statistics. My knowledge of statistics is frankly very limited. I took like one undergraduate class in statistics, and that's about it. But I got good grades, but I wasn't really super satisfied with my knowledge of the topic. So I decided to do some private self-studying for myself, and I am going to record some of this for you guys to listen to. I hope you all enjoy, but you probably will not. Okay, so, yes, and I also have RStudio. Let's see. Yes, RStudio open right here, and I will be doing all of my statistics whenever that is applicable in here. So that is all for this right now. Let's dive right in. I have already started some of the textbook, but I'm going to go ahead and start from the beginning. I read a little bit of this section right here, section number 2, getting started with R, and I got to about like over here, hereabouts. However, I am going to start from the beginning just so it's a little more interesting. So, in order to make this just a little bit more interesting, I have decided to at least consider narrating some of the textbook. However, if I am told to be quiet, it is in the middle of the night, by the way. I do have a setup which should help prevent some noise escaping, but if someone tells me to be quiet, I will absolutely shut my mouth. Anyways, I will attempt to narrate this book. However, I must say that you should probably not expect audiobook quality. I am just doing this for the sake of, just saying what it's like. I may or may not stick with this for the rest of the live stream. Who knows? To the surprise of many students, statistics is a fairly significant part of a psychological education. To the surprise of no one, statistics is very rarely the favorite part of one's psychological education. After all, if you really loved the idea of doing statistics, you'd probably be enrolled in a statistics class right now, not a psychology class. So, not surprisingly, there's a pretty large proportion of the student base that isn't happy about the fact that psychology has so much statistics in it. In view of this, I thought that the right place to start might be to answer some of the more common questions that people have about stats. A big part of this issue at hand relates to the very idea of statistics. What is it? What's it there for? And why are scientists so bloody obsessed with it? These are all good questions when you think about it, so let's start with the last one. As a group, scientists seem to be bizarrely fixated on running statistical tests on everything. In fact, we use statistics so often that we sometimes forget to explain people why we do. It's a kind of article of faith among scientists, and especially social scientists, that your findings can't be trusted until you've done some stats. Undergraduate students might be forgiven for thinking that we're all completely mad because no one takes the time to answer one very simple question. Why do you do statistics? Why don't scientists just use common sense? It's a naive question in some ways, but most good questions are. There's a lot of good answers to it. But for my money, the best answer is a really simple one. We don't trust ourselves enough. We worry that we're human and susceptible to all of the biases, temptations, and frailties that humans suffer from. Much of statistics is basically a safeguard, using common sense. To evaluate evidence means trusting gut instincts, relying on verbal arguments, and on using the raw power of human reason to come up with the right answer. Most scientists don't think this approach is likely to work. In fact, come to think of it, this sounds a lot like a psychological question to me. And since I do work in a psychology department, it seems like a good idea to dig a little deeper here. Is it really plausible to think that this quote-unquote common sense approach is very trustworthy? Verbal arguments have to be constructed in language, and all languages have biases. Some things are harder to say than others, and not necessarily because they're false. Example, electrodynamics is a good theory, but hard to explain in words. Close parentheses. The instincts of our gut aren't designed to solve scientific problems. They're designed to handle day-to-day inferences, and given that biological evolution is slower than cultural change, we should say that they're designed to solve the day-to-day problems for a different world than the one we live in. Most fundamentally, reasoning sensibly requires people to engage in induction, making wise guesses and going beyond the immediate evidence of the senses to make generalizations about the world. If you think that you can do that without being influenced by various distractors, well, I have a bridge in Brooklyn I'd like to sell you. Heck, as the next section shows, we can't even solve deductive problems. That is, ones where no guessing is required without being influenced by our pre-existing biases. The curse of belief bias. People are mostly smart. We're certainly smarter than the other species that we share the planet with, though many people might disagree. Our minds are quite amazing things, and we seem to be capable of the most incredible feats of thought and reason. That doesn't make us perfect, though, and among the many things that psychologists have shown over the years is that we really do find it hard to be neutral, to evaluate evidence impartially, and without being swayed by pre-existing biases. A good example of this is the belief bias effect in logical reasoning. If you ask people to decide whether a particular argument is logically valid, i.e., the conclusion would be true if the premises were true, we tend to be influenced by the believability of the conclusion, even when we shouldn't. For instance, here's a valid argument where the conclusion is believable. Premise 1. No cigarettes are inexpensive. Premise 2. Some addictive things are inexpensive. Conclusion. Therefore, some addictive things are not cigarettes. And here's a valid argument where the conclusion is not believable. No addictive things are inexpensive. Some cigarettes are inexpensive. Therefore, some cigarettes are not addictive. The logical structure of argument 2 is identical to the structure of argument 1, and they're both valid. However, in the second argument, there are good reasons to think that premise 1 is incorrect. And as a result, it's probably the case that the conclusion is also incorrect. But that's entirely irrelevant to the topic at hand. Well, thank you for mentioning, Mr. Author. An argument is deductively valid if the conclusion is a logical consequence of the premises. That is, a valid argument doesn't have to involve true statements. On the other hand, here's an invalid argument that has a believable conclusion. addictive things are inexpensive. Some cigarettes are Premise 1. No addictive things are inexpensive. Premise 2. Some cigarettes are inexpensive. Conclusion. Therefore, some addictive things are not cigarettes. And finally, an invalid argument with an unbelievable conclusion. Premise 1. No cigarettes are inexpensive. Premise 2. Some addictive things are inexpensive. Conclusion. Therefore, some cigarettes are not addictive. Now, suppose that people really are perfectly able to set aside their pre-existing biases about what is true and what isn't, and purely evaluate an argument on its logical merits. We expect 100% of people to say that the valid arguments are valid and 0% of people to say that the invalid arguments are valid. So, if you ran an experiment looking at this, you'd expect to see data like this. If the psychological data looked like this, or even a good approximation to this, we might feel safe in just trusting our gut instincts. That is, it'd be perfectly okay just to let scientists evaluate data based on their common sense, and not bother with all this murky statistics stuff. However, you guys have taken psych classes, and by now you probably know where this is going. In a classic study, JSBBT Evans, Barston and Pollard, 1983, ran an experiment looking at exactly this. What they found is that when pre-existing biases, i.e. beliefs, were in agreement with the structure of the data, everything went the way you'd hope. Not perfect, but that's pretty good. But look, what happens when our intuitive feelings about the truth of the conclusion run against the logical structure of the argument? In this case, if the argument is valid and yet the conclusion feels true, 92% would say that it is valid, whereas if the conclusion feels false, only 46% would say valid. And if the conclusion feels false again, and the argument isn't valid, only 8% would say valid. Oh dear, that's not as good. Apparently, when people are presented with a strong argument that contradicts their pre-existing belief, we find it pretty hard to even perceive it to be a strong argument. People only did so 46% of the time. Even worse, when people are presented with a weak argument that agrees with their pre-existing biases, almost no one can see that the argument is weak. People got that one wrong 92% of the time. If you think about it, it's not as if these data are horribly damning. Overall, people did do better than chance at compensating for their prior biases. Since about 60% of people's judgments were correct, you'd expect 50% by chance. Even so, if you were a professional evaluator of evidence and someone came along and offered you a magic tool that improves your chance of making the right decision from 60% to, say, 95%, you'd probably jump at it, right? Of course you would. Thankfully, we actually do have a tool that can do this, but it's not magic, it's statistics. So that's reason number one why scientists love statistics. It's just too easy for us to believe what we want to believe. So if we want to believe in the data instead, we're going to need a bit of help to keep our personal biases under control. That's what statistics does. It helps keep us honest. As an aside, I would just like to mention I have recently read a book titled How to Lie with Statistics, which is a little bit funny because there are many ways in which you can just absolutely misportray the data with statistics. In line with this, if one does not understand how statistics work, then they're going to get lied to by said statistics, and they're going to be led along by a string pretty much all the time. To help prevent this is essentially the reason why I wanted to learn statistics, and so that I could improve some of my scientific research. Okay, moving into the next section. Cautionary Tale of Simpson's Paradox. The following is a true story, I think. In 1973, the University of California, Berkeley, had some worries about the admissions of students into their postgraduate courses. Specifically, the thing that caused the problem was that the gender breakdown of their admissions, which looked like this, that is, it had 8,442 male applicants and 4,000 321 female applicants, and 44% of the men were admitted, whereas only 35% of the females were admitted. And they were worried about getting sued, understandably, for this. Given that there were nearly 13,000 applicants, a difference of 9% admission rates between male and females is just way too big to be a coincidence. Pretty compelling data, right? If I were to say to you that these data actually reflect a weak bias in favor of women, sort of, you'd probably think that I was either crazy or sexist. Oddly, it's actually sort of true. When people start looking more carefully at the admissions data, they told a rather different story. Specifically, when they looked at it on a department-by-department basis, it turned out that most of the departments actually had a slightly higher success rate for female applicants than for male applicants. The table below shows the admission figures for the 6 largest departments, with the names of the departments removed for privacy reasons, on the campus. Remarkably, most departments had a higher rate of admissions for females than for males, yet the overall rate of admission across the university for females was lower. Lower than for males. How can this be? How can both of these statements be true at the same time? Here's what's going on. Firstly, notice that departments were not equal to one another in terms of their admission percentages. Some departments, e.g. engineering/chemistry, tend to admit a higher percentage of the qualified applicants, whereas other, example, English, tend to reject most of the candidates even if they were high quality. So among the 6 departments shown above, notice that Department A is the more generous, followed by B, C, D, E, and F, in that order. Next, notice that males and females tended to apply to different departments. If we rank the departments in terms of the total number of male applicants, we get A followed by B followed by D followed by C followed by F followed by E. That is, the easy departments. This is really not a readable. It's really hard to read in audiobook form. Okay, I know I said I would not read this like an audiobook, but I kind of am. Okay, so just to be clear, this is my quote-unquote slop channel. The intention of this is to basically just post additional live streams or videos which I really don't want to do anything with. And mostly just to improve my videography skills, again, as I already said, and also just to serve as a potential for getting revenue on crap which I don't really want to post on the main channel. By the way, my main channel is Sir-based. That's it. Sir-based. Not Sir-based slop, but Sir-based. Now, let's see. Shall I continue with narrating to myself as I am reading this? Would that be a good idea? Well, allow me to think about this for a moment. I am going to be silent for the next few seconds, so please pardon me as I do that. Okay, so I have made up my decision. Narrating this, frankly, takes a lot of my cognitive effort, especially if I'm going to be doing it well. So for the most part, I'm mostly just going to be pretty much silent, and then if I come across a note which I want to take note of, as you do with notes, I will probably talk about it. But for the most part, I'm just going to be silent for now. So, if memory serves, I believe that there is actually essentially, what's the word? Taking over on the part of female applicants of many STEM fields. I frankly do not know why this is, and I have not looked into it, but I would like to look into it in the future. Um, just as like an interesting note. Here it says that when the author started writing, on their lecture notes, they took 20 of the most recent news articles posted to the ABC News website. Of those 20 articles, it turned out that 8 of them involved a discussion of something that she would call statistics, and 6 of these were just a complete mistake. Which is, honestly, that does not surprise me whatsoever. And is again another reason why I genuinely want to learn statistics, because I seriously do not trust anything that most people say with respect to it. And again, just for any of the 0 people tuning in, for good reason, by the way, any of the 0 people tuning in to this live stream, again, I am reading Learning Statistics with R, which is a copyright-free and open to redistribute or share thing. You can see this at learningstatisticswithr.com, and it is by Danielle Navarro. So returning back to the textbook which I'm reading. So, I am, of course, aware of the climate change controversy. I personally have not looked into it, though I personally am not sure as to which, like, answer is actually correct. I would like to look into this in the future, though. That's funny. Alright, guys, we got a total of 0 viewers. Alright. I can't believe that no one would want to watch this. I mean, like, come on, this is so interesting. I'm just reading a textbook. Wow. Yeah, I suppose another reason why I essentially wanted to do this, I kind of already mentioned this before, but there's something a little bit unnerving in a way about just talking to yourself. I mean, not just talking to yourself by yourself, because I talk to myself all the time, but talking to yourself with the expectation that some unknown person or unknown people, in fact, an unknown multitude of people, could potentially listen to what you are saying. Like, that's just a little bit unnerving. And since it is essentially my interest to become a YouTuber, I suspect my first videos are going to be absolute crap, let me just say that. I know I'm great at advertising, but since my first videos aren't going to be the greatest, and since I'm not going to have necessarily the opportunity to create videos that frequently when things first start out, I reckoned it was a good idea that I get in the habit of, well, that I just get comfortable with talking before a camera or talking before a mic, because that is really something that just feels kind of just weird in a way. So, without further ado, I would like to, I guess, continue with my reading of the textbook. And by the way, just for reference, all of this content here is something which you would learn in a research methods class for psychology, which I have also taken. Um, I did not count it as my explanation previously when I was talking about statistics, because, I don't know, I guess I just mentally partitioned these two concepts separate from one another, but legitimately, research methods does, of course, share a lot of similarities and a lot of overlap with statistics. In fact, you kind of need to understand statistics in order to take research methods, which I have taken in the previous semester. So I guess technically I have taken 2 classes for this, and by the way, just reading this explanation here, I would say that's very close. In fact, I would say that it's like spot on with the explanations that I received in both my statistics and my research methods class. So, yeah. Anyways, I'm going to move on. By the way, because I have taken a research methods class, a lot of this is legitimately just review, which I don't really see anything wrong with. I do understand all these concepts, and I have already memorized quite a few of them. I am just rereading this though, just in case that I missed something, because there was one time during class where my professor was talking about the different scales of measurement. All right, and where I just asked a question like, hey, wouldn't it be possible? Well, I forgot the exact question, but the way that he answered really cleared up the thing which was there. And I'm just thinking here, well, it's very well possible that I may have missed something, or I may have failed to ask a question which would have really, really clarified the content. That's just a very inarticulate way of saying, I don't want to miss things. My question here is, are there any other scales of measurement? I would really like to look into this. It seems kind of interesting. Are there other scales of measurement? I'm going to stay in this tab for just a moment because when I was Googling something off screen, it literally showed my IRL location, so I don't want to accidentally dox myself. So I'm just going to do this off camera for just a moment, do some off camera mining. Okay, so apparently they're called the Stevens scales. At least that's what AI says. I'm not sure if I trust this. Which describe the level of detail and mathematical properties of data. Analyses are appropriate. Other related concepts like discrete versus continuous variables and variations like count data. What are you even trying to say, AI? Okay, so AI is essentially just saying here, and by the way, it's not showing my location, so I feel comfortable showing this. Let me just... There we go. Okay. Here it's talking about how, it's broken down into like the 4 main different scales. So you got nominal, ordinal, interval, ratio, and then there are other related classifications such as discrete versus continuous, and whatever this means. Okay, so I wouldn't actually view these as additional scales of measurement within the same framework, in the same way that you would not consider, let's see. Yes, okay, so take numbers for example. You can classify numbers according to even or odd. Okay, those are 2 different ways of classifying this. So, using this analogy here, we could say that this kind of classification is like an even versus odds classification. Whereas this kind of classification, let me go back to numbers here, I believe that there is another form of classification for numbers wherein you classify it as perfect or ideal, abundant, and I'm forgetting the terminology here, but I'll just use the word privation even though that's not correct. And anyways, Perfect numbers is where if you add each of the individual numbers before it together, and if you add them all together, the sum is the number itself, which is kind of interesting. A good example of this would actually be the number 3, I believe, because you have 2 and you have 1, and then you add those together, and then you get the number 3, which is the number itself. Okay, so that would be a perfect number. An abundant number, or a superfluous number, I forget the name, would be one where if you add all the individual numbers before it together, you get more than the number itself. And I guess a privation number, though that's the wrong term, is where if you add them all together, you get less than the number itself. So these are two different ways of classifying numbers, but that's it. It's not, I'm looking for an additional classification or an additional, I guess, variable or value, which you can get for this classification of numbers. To go back to the even example. However, it seems I am not finding that, so I am going to return back to the textbook real quick. What are you doing? There we go. Okay. I suppose here's another interesting just thing to talk about, and that would be this. It would seem that on the ratio scale of measurement, negative numbers aren't really possible. And it would seem that on the interval scale, well, the interval scale is just the arbitrary scale which you create, which you set, because there isn't really a good known starting point with which to declare, with which to say 0 is. Now, the author raised the example of temperature, and that is why you have like Celsius. 0 degrees does not actually mean 0 temperature, because if you look at what temperature is, it's essentially just the atomic oscillation of, well, atoms and particles, and the higher the temperature, the faster and more vigorous said fluctuations are, whereas the lower the temperature, the slower said oscillations will be. Okay, now since that is the case, you could theoretically posit that a temperature of 0 would be the point where there is 0 subatomic or like atomic oscillation of the atoms. Okay, you could absolutely say that, but at the time that I believe that people like Fahrenheit, and I think that's the guy's name, I don't know if it is or not, the fellow who came up with Celsius, they probably were not able to measure the true, what is now considered to be absolute 0, and that would be in the Kelvin scale of the Kelvin scale of measurement, not the Kelvin scale. Actually, I think that's right, the Kelvin scale of measurement. Yes. Also, another reason why measurements like Fahrenheit and Celsius somewhat arbitrarily set 0 to be far above the actual value of 0 is because it's just a lot more convenient. Let's just be honest here. It would be very, very annoying doing your day-to-day calculations of temperature using the Kelvin scale of measurement. That would just be stupid. So I'm glad that we do that, but it technically is not in line with reality if you want to declare 0 to be actual 0. So, with that said, So I genuinely like the definition here for continuous versus discrete variable. The previous textbook which I took in my first statistics class was unironically let's see, well, I forget the exact textbook, I'm sorry, but it was through the Pearson program, the Pearson statistics program, and let me just say this, it absolutely sucked. It was horrible. I did not enjoy it at all. And the definitions and all the explanations were like the most verbose garbage I have ever seen. I will compliment the author here. They have a very readable style, and it makes sense what they are saying. And what I am noticing, having taken a statistics and a research methods class, is it seems to be very on target with all the information that they have said. Comparing it with the other information which I received in my other classes, this seems to be very on target. We will see if this remains the case throughout, but I have high hopes, I must admit. And I suppose just to put forth something of an explanation, I will try my best to explain. I suppose just put forth something of an explanation for what the Pearson textbook definition for this was like. I believe that it stated, if I recall correctly, that for a variable to be discrete, it has to be both finite and countable. Now, that's kind of a silly definition, and the way that they explained it really is not at all intuitive. I like this explanation because it is much more intuitive. But anyways, finite means that if you have a set, like you actually have to, if you can count like one single variable or one single value per second, there has to be a point where you could come to an end result. I guess that's kind of what it means. And I guess you could really just collapse finite and countable into one, because they essentially, like, yeah. So I don't really like the Pearson textbook. Definitely, it really was not good. Basically, that's just what it means. Like, if you were counting them one by one, then there would have to be a point in time where you would come to an end, or where you would stop. Okay, and there can be a few different reasons for why that is, or for how that can go awry. For example, let's say that you have the two values, 1 and 2. Does that mean that if you count at if you count one value every second, that if you go from 1 to 2, that you will necessarily reach the end? No, not necessarily. Here's the thing. You can also have decimal points in between them. Okay, well, let's say if there's like 1, 1.5, and then 2. No, because there are also more. You can have 1, 1.25, 1.5, 1.75, and then 2. And you can keep expanding this, and you can in fact declare as many arbitrary and irrational numbers as you would like in between 1 and 2. And that's one way in which a variable can be continuous or not discrete. Another way is just 1 and infinity. The values here are between 1 and infinity. That's another way in which things can be not continuous. Okay, so with that said, I like this definition because it seems very easy to grasp, like conceptually. You don't really have to unpack it that much, and you don't really have to conceptualize too hard. It just like makes intuitive sense. Okay, with that said, I guess I would like to move on. Okay, I'll be honest with you. I really like this distinction, and I really like how the author is actually going into this. I did not actually hear any of this in either of my classes. I'll be honest with you. So I am genuinely impressed. This is very good. This too, I think, is actually a very good discussion because they're pointing out some contradictions with the system or with the stuff which they have put forth, which you very rarely see a textbook do. I'm not an expert in this field, but I am very, very impressed, I'll be honest with you. Hmm, interesting. how this really is just a very summarized version of a research methods class in this first section here. Like, it appears that the first, like, 33 pages or so is basically just like a research methods class, which I'm honestly not mad about. I think this is very helpful, but I must say that it's probably most helpful for social science, especially psychology students. So, well, that's that, folks. Okay. Hmm. I was not aware that the more modern name was outcome, or rather, the more modern name is outcome versus predictor variables. I was honestly taught on the dependent versus independent variable distinction. Okay, so I'm going to go ahead and note this down. Just as an aside, completely unrelated to what we're doing right now, I think it would actually be pretty interesting for me to examine with these live streams how long it takes for me to lose focus of the material. Because, like, pretty naturally, I'm gonna bet that, like, my reading speed, when I first start reading a textbook, when I first start reading an article, or whatever it might be, is probably fairly slow within, like, the first few seconds, because, like, my brain's getting adjusted. But then it reaches its peak relatively quickly. And then from there, my prediction is that it would probably kind of like teeter off over time as I continue to read the text. Um, and if I did that, I could possibly get some kind of calculation or statistic or whatever, which measures what the optimal amount of time for me to read a book would be. Okay, and that honestly I think is pretty interesting. Now, one interesting note which you have to take into account with something like this is that it really does vary depending on the subject material that you are reading. And not only that, it also, not only just the subject material, but specific sections within the subject material. For example, in my introductory chemistry course, which I took like the previous semester, I am like a sophomore by the way. In my introductory chemistry course, which I took the previous semester, like the hardest chapter in that entire book, and I was reading the OpenStax book by the way, the hardest chapter, which is free and online, the hardest chapter in the entire book, by the way, was legitimately the quantum mechanics chapter. The two chapters before it were super easy. Those are the first two chapters of the book, and then every chapter after that were fairly easy as well. But that chapter by itself was like the hardest thing in the universe. So, with this example in mind, it's very easy to imagine how various other books may well also be subject to the same thing. Although, hopefully, especially if you're reading like fiction or, um, I don't know, I guess rather homogenous nonfiction, like nonfiction which is homogenous with respect to difficulty, you can also generally generalize that as well. But I don't know how this would work in more difficult, in less and more heterogeneous books. Just to use a fancy term. So we will see about that. I just thought that was interesting. Anyways, getting back to reading. Truthfully, the predictor response variable is one of the terminologies, or one of the terminology, wrong term, is one of the words which I heard used in my research methods class. But I understand why they're using outcome. I'll probably stick with like response variable because I mean it's used in R, and also that's just what I'm used to. So I'm probably gonna stick with that honestly. Now, interestingly, here it says that the difference between experimental and non-experimental research is the degree of control that the researcher exercises over the people and events in the study. I think that this is a good definition. I would just like to add here that I think you can actually potentially say that experiments and non-experiments actually exist on something of a continuum, even though that's not generally how it is thought of. Like you could technically say that a polyvariate, oh, pardon me, not polyvariate, multivariate research study in which you examine a bunch of different variables and then control the ones which aren't really, which you don't want to look at for that particular analysis. You could say that controlling those variables actually, in a way, leans more towards the experimental side of it, even though you're not doing a physical experiment in the true sense. You are getting closer to that degree of being able to demonstrate some kind of causation. So I don't know, but I personally like that. I personally like this distinction, or rather this non-distinction, and instead viewing things as a continuum. Although, of course, with like multivariate research, you're not really able to control everything in the way that you would with an experiment, which is why, for good reason, experiments are essentially the gold standard of research. So I just thought that was interesting, and I'm just going to move on. This terminology isn't exactly the most intuitive, because you could certainly just say that, the non-experimental research is research where you don't do an experiment. But here they're saying that it is any study in which the researcher doesn't have quite as much control as they do in an experiment. Which, I mean, okay, I guess. I guess you could say that. But I don't know. I think that. Oh, pardon me. I think that the terminology here could be a lot better. Now, for those of you who don't know, that there was my timer to stop studying statistics, and likewise to also stop streaming. So I am going to stop very soon. And let me just look here at the number of people watching. Are you telling me that no one wanted to tune in at like late in the evening US time? Late in the evening US time for a statistics live stream where there's not even any narration or anything? Wow, that's crazy. Well, anyways, thank you everyone, or rather nobody, for listening, and I would like to now end this stream. That is all. SirBased signing out.